plus L minus K. Wonderful. Okay. So you see the thinking process, right? That from the big game, if you haven't seen the random variable before, that's where you move from here to here. You can move that, and then the rest is simple computation. So can you follow it? Okay. So if you can follow this, you can do the homework. Alright, so I have this simple, right? So that gives me that. My question now to you, if I tell you that, I give you that summation, it gives you one number, right? One number. In that number, what variable does it depend on? Depend on L? Depend on M. What are the variable that we're going to depend on? And anything else? Only M. Only M. Is that clear, right? You see, it has a K and L here. It has H and X. K and L are two dominant variables, as I said. The sum washes it out. So this thing here is only depend on X and H. And so because of that, but you can see that this thing here, it doesn't now, it's no longer depend on N. It's only depend on N. And if it doesn't depend on N, then Y, what do I have to do? So Y is just stationary process because it's two. So this thing here, I can denote that it's equal to Y, gamma of Y, and it is equal to the function of M. Right, that is. And this thing here is I define definition. I can know that now. So you have this relationship. The relationship now, I have a signal, I have an output in the deterministic sense. That means for one instant of that signal, I can compute the output. But now having a sum of them, so that means now I can describe them in the Y-sense stationary process by this autocorrelation function. Then that autocorrelation function will tell me now everything now is fixed. I can get the autocorrelation function of the output. Okay, without that good. Now, good first step. As we know, signal processing relies not just the signal in time, but also the frequency. Right? The frequency. So now I want to define, I have this autocorrelation function. I can also compute it in the Fourier domain. Right? So we can define, so we use notation, right? I have an autocorrelation function. What it is really just a sequence, a signal in M. So we can always define gamma XX of omega equals as our definition. So this is we define a summation in M of gamma XX in M and e to the minus j omega m. Right? Simply the Fourier transform, this is now Fourier transform of this. Okay, I have this. Now what we want to write is the relationship between this equation in time. Also in frequency domain. Right? In frequency domain. So here's another good exercise, but now we need to move ahead and I do it here. So I have that signal and I have the signal outlet. So maybe before we move to the frequency domain, so the frequency domain, let's do it in time. In time here, I have this equation here. So this is gamma and maybe this, we put that equal to, so what should we do? Maybe I can put constant, I put the k outside here. So I have a summation in h of k. And I put this k here. And then I put inside this is a summation in L of h of L. And I have h of L, and I have gamma of x of m plus L minus k. Right? I can data set it. What is this summation? Can you recognize this? It's like a correlation, right? Correlation. But now my trick is, you know, if I want to write something in Fourier domain, if I can find a convolution in Fourier domain, it becomes a multiplication. Right? So my line of attack now is I want to map this into a convolution. I want to map it into a convolution. So you learned the trick in one of the exercise yesterday. One trick that can turn it into a convolution. Okay, let me define something that has a flip, right? So if I would define, define h, use a bar, right? Hn of L equal to h of minus L. Alright? So we define that, then what I can do now is I can put just simply minus and minus here. Okay?
Could we take the L out and so we can
Say, yes. You might say one, but you have to do another one.
Because we have minus k, so but after that we will have
right, yeah. Okay, someone only sees the proof. Okay. Yeah, we haven't had this thing. Okay. But a very good observation, yes. So yes. I think someone already smelled the convolution, right? Word for the convolution. Okay, so now the thing inside the bracket now, can you recognize that convolution? So what's the convolution? It is a convolution of this thing here is a convolution of h, combined with the gamma of h bar, combined with this autocorrelation of h, right? And what divided at what point? M minus k. Everyone see that, right? Because when you do the convolution, like yn equal to this, that means n, right? So simply look at this, and the autocorrelation is that block is out. That's why we have to make this minus sign and cancel this. It doesn't depend on L anymore. Okay, so I have that, and now I have a summation in k of hk. So that is one signal, that is another signal. So now that's why those friends tell you that, yeah, so now I have this thing, simple convolution of this with that. So now what I have here is I just simply have h combined with this, and you need to show the convolution is having the distribution. So let me h bar combined with y of x. You need to see that I can draw this, but okay. For now, I will keep this. And what value now? N, right? We're going to get k, the one variable, k plus n minus k equal to n, so that I pop out that. So this is very beautiful, right? This y, gamma y simply equal to taking this, convert